Hello everyone, and in this video today, we're going to look at deriving the two different formulas. One, the sum of an arithmetic series, as you can see here on the screen. So we're going to derive this formula here. And then secondly, we're going to derive the equivalent expression for the sum of a geometric series as well. Okay, this is something that you could be asked to do at A-level, and it comes up and it's usually worth about 4 marks, something like that. It's one of the set kind of proofs that you need to know. Okay, so let's have a look. So first of all, what we're going to do is we're going to try and prove this formula. So derive this formula from first principles. So we're going to start off by writing down an arithmetic progression. So an arithmetic series rather is going to be Sn is equal to A is the first term, okay? The second term is A plus D, which is the common difference. Then the next term is going to be A plus 2D, A plus 2 lots of the common difference. And then we carry on like that, adding more and more terms, okay? So the next one would be A plus 3D and so on. I'll just put some dots in the middle just to show that we're approaching the other end of the sequence now. And then at the other end of the sequence, the penultimate one is A plus n minus 2 times D. And then the last term in the sequence is A plus n minus 1 times D. Okay, so that is our arithmetic series where we're adding together all of the terms. Okay, so we've got the first one is A plus D, A plus 2D, A plus 3D, and so on, and then all the way up to the last one, which is A plus n minus 1 times D. The reason this is n minus 1 times D is because the number of times we've added the common difference is 1 less than the number of terms that there are, because the first term is just A. So what we do in this one is we start it off by writing it out forwards, and then we're going to write it backwards underneath as well. Okay, so we're going to write the sequence backwards underneath. So Sn, I'm reversing the order. A plus n minus 1 times D, the last term. The penultimate term was the second to last term was A plus n minus 2 times D. And then plus dot 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 all the way down to the first two, which was A plus D, and then the very first one was A. So we've just written the sequence forwards and then underneath written the sequence backwards. Now we're going to add these two sequences together. Okay, we're going to add them together. So we've got A. Okay, so that's one pairing, and we add that together. And then this is going to be another pairing. Okay, and then over here we're going to have these two. So I'm just pairing up, matching up the first and last, and the second from last, and so on. So when we add these two together, the first and the last, we end up with 2A plus n minus 1 times D. Okay, and then we've got 2 lots of the series now because we're adding Sn, add Sn, so we've got 2 lots of Sn. This next pairing, what does it add up to? A plus A is 2A again. And then n minus 2 times D plus D is n minus 1 times D. So that goes to n minus 1 times D. And then we'll just put the dot, dot, dot. Let's see what happens when we add these two up. Again, we get A add A is 2A. And n minus 2 times D add D goes to n minus 1. So n minus 1 times D. So 2A plus n minus 1 times D. And then finally, you can probably guess see what's happening now. This final pairing also gives us 2A plus n minus 1 times D. So what we're saying is that when we write the sequence forwards and we write the sequence backwards and we add them together, we end up that every single term comes to 2A plus n minus 1 times D. Now, because this series has got n terms, we've got n lots of 2A plus n minus 1 times D. So what we do is we can say we've got all of these come together. We can just replace them by saying we've got n lots of 2A plus n minus 1 times D, because there are n terms in the sequence. Okay, so we've got n of them. And then finally, we just divide the whole thing by 2, and that's the whole formula derived. So we end up with Sn is equal to n over 2 times 2A plus n minus 1 times D. And that little proof there would be 4 marks, really well worth learning for the exam. So just to recap, you write it, the series forwards, you write the series backwards, you add the two series together, you find out that every single term in this combined addition gives you 2a plus n minus 1 times d. Because there are n terms in the series, there are n of these, so you place that by n times 2a plus n minus 1 times d, and then finally you divide it by 2. Okay, so that's one that you could be asked to derive. Okay, let's change our attention now, move our attention to the sum of a geometric series. Again, we could be asked to derive that one. So let's have a look at how we would derive the sum of a geometric series. A little bit different this time. So we're going to write down our geometric series, same kind of thing that we did before. So this time we have our first term is a, and our next term is a times r, the common ratio. The next term is a times r squared, and so on. We'll do the same as we did before, put some dots there. We'll do the second to last one is a times r to the n minus 2. And then the very last one is a times r to the n minus 1. Okay, again, you know, when I was first learning this, it sometimes used to confuse me about why is it r minus 1 at the end there. And the reason that it's r to the power of n minus 1 is because we've multiplied by r 1 time less than the number of terms that there are in this series, because the first term was just a. So that's why it's minus 1 there. We've times it by r n minus 1 times. Now for this one, what we do, we reversed it on the arithmetic one, but for the geometric, we multiply the series by r. So we write down r times Sn is now going to equal ar plus ar squared. And then we're going to have plus ar cubed plus dot, 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 dot. That's going to go to ar to the n minus 1 now. And then the last term is now going to become ar to the n, because we've multiplied everything by r. And then with this particular proof, having done that, having times that series by r, we now subtract these two expressions. So we have now Sn minus r times Sn over here on the left. And now when we take these away, this is it's like a technique from A-level further maths called the method of differences. You don't need to know that if you're just doing just A-level, but this is kind of like what's happening. So when we subtract these, we find that diagonally here, loads of these pairings all cancel out with each other. Okay, and I'm just kind of for effect showing you this, yeah. So basically that cancels because you're a to the a times r minus a times r, ar squared minus ar squared. So they all basically disappear. And when you subtract them, you're only left with this top left term and this bottom right term. So you're left with a minus ar to the n. That's all you're left with, okay? So what we do now is we're going to, on the left-hand side, factorize out our Sn. So Sn, open brackets, 1 minus r. Over on the right-hand side, we're going to factorize out our a. So that gives us a, 1 minus r to the n, like so. And then finally, we're just going to divide by the 1 minus r. So we have Sn is equal to a, open brackets, 1 minus r to the n, all over 1 minus r. And that is our formula derived for the sum of a geometric expression. So a little bit different to the other one. The arithmetic, we just times everything by r, and instead of adding them, we subtracted them. Okay, so that's how that one works. And again, that would be worth another 4 marks. And it's a really nice little thing just to have those memorized, just to pick up those extra marks should they arise in the exam. I hope that you found that helpful, and I'll see you in the next video.